So we're continuing with this problem, and we got to the generating function for, remember our differential equation was x squared plus 1 y double prime minus 6y is equal to 0. And we finally got to this generating function, and we also said that C3 was equal to, let me go back up just to remind myself, C2 was equal to 3C0, excuse me. So C2 was equal to 3C0. We also said that C1 was equal to C3. All right, so we're going to hold on to this information because all this is necessary for us to be able to continue to solve. And now what we're going to do is we're going to use our method of iteration. All right, so we have k equals 0, and we have c sub k plus 2 is going to be equal to c sub k opposite, k minus 3 times k plus 1. All right, so and a lot of students always ask me, how many different iterations do we have to go through? And my response is probably enough just to make sure that you know the pattern. So sometimes you can see it really quickly. Sometimes it might take you 8 to 10 iterations to go through. Remember, it's just algebra, so it's more just tedious than difficult. All right, let's plug in 0 for c sub k, or for k, excuse me. So that gives us that C2 is the opposite of C0, 0 minus 3 over 0 plus 1. And if we simplify that, we're not going to get a shocking answer to that. We're going to see that that's going to be equal to 3C0. And why is that not shocking? Well, remember when we solved all of those coefficients, we saw that C2 was equal to 3C0. This is more of just a check at this point. If those two things don't equate to one another, then you probably have to go back and you probably have to try to redo your generating function to make sure that your occurrence relation truly is algebraically correct. Now, if we plug 1 in, we should get C3 is equal to C1. So let's see if that happens. So C3, so we're just substituting 1 is there, is going to be equal to the opposite of C1, 1 minus 3 divided by 1 plus 1. Well, that gives us the opposite of negative 2, which is 2. 2 divided by 2 is going to be 1, so we do indeed end up with C1. All right, so that's a good thing. If those two things are off, we need to go all the way back and we need to redo it. All right, fortunately for us, we don't have to. All right, so that's good. Now let's plug in 2. That gives us C4. So that's the opposite now of C2, 2 minus 3, divided by 2 plus 1. And we get the opposite of negative 1, which is 1, over 3. So I think this should work out to be 1/3 C2. All right, but recall that C2 was equal to 3C0. So in fact, we get 1/3 times 3C0, which is C0. All right, so that works out really nicely for us. All right, so it just seems like that this one's working out really well for us. All right, it's even going to work out even better. So let's continue with this method of iteration. Now we're not really seeing a pattern yet, all right, because we kind of get things jumping around, but eventually we will. All right, so C5, that's going to be the opposite of C3, 3 minus 3 over 3 plus 1, but we know 3 minus 3 is 0. That means the whole thing, or the whole expression, is just going to go to 0. So C5 is equal to 0. All right, so that's kind of helpful, as we'll see. C6 is going to be equal to the opposite of C4, 4 minus 1 over 4 plus 1, and we get this negative 3/5. I'm sorry, this should be 4 minus 3, excuse me. So let's go back. This should be a 3. All right, so it's going to be negative 1/5 C4. But we remember that C4 is equal to C naught. So that's really minus 1/5 C naught. All right, so that's why, again, that's why it's called a recurrence relation. You use the previous instances to generate these other functions, or these other portions of the function. All right, C7 is going to be really easy because we get the opposite of C5, 5 minus 3 over 5 plus 1, right? And we don't have to go any further because remember we said that C5 was equal to 0? So it just becomes 0. Because remember, this is going to be 0, and 0 times whatever is just going to make the whole thing go away. So it looks like that there's a few terms that work out. And then it looks like after that, like for instance, we have C1, which is C1, we have C3, and then we have C5, which is 0, and then we have C7, which is 0. Now let's just do a couple more of these. All right, and I'll show you how to write the answer after that. So let's just do 6 and 7. 6 is going to give us C8, which is the opposite of C6 times 6 minus 3 over 6 plus 1, which is going to be negative 3/7 C6, but you recall that C6 was 1/5 of C naught. So that's going to be negative 3/7 times 1/5 C naught, and that's ultimately going to be equal to, and this should be a negative 3/7, with a negative 1/5, yep. So that's going to be 3 over 35 C naught for C6, or for C8, excuse me. All right. And just one last. So for 7, C9 is going to be equal to the opposite of C7, and we can stop right there because we know C7 is a big old 0. Times it doesn't matter, over it doesn't matter. C7 is 0, so that's going to be equal to 0. So what does that tell us? Okay, well it tells us that all the odd terms are going to be equal to 0 except for C1 and C3. Now remember, C1 is just C1 and C3 is C3. All right, how do we write the solutions to this? Okay, so now we have all of our iterations. All right, now remember, all the way back at the beginning of this problem, we had this series, y equals series, n equals 0 to infinity, c sub n x to the n. And now what we're seeing is that we found these coefficients, C9, C8, C7. These are the coefficients of the powers. So this is the coefficient of the power x to the 7th. This is the coefficient of the power x to the 8th. This is the coefficient of x to the 9th, etc. All right? So what we're going to do is we're just going to look all the way back, and we're just going to put each of those coefficients in front of each of the successive powers of x. And we're going to split them up into even and odd terms, because if you look back, notice that the even terms all match up to C0. So C2 has a C0 in it, C4 has C0 in it, right, etc. All right, C6 has C0 in it, etc. All right, so let's do our first solution. I'm going to call that y1. And y1 is going to be all of the even terms. All right, so what's that going to be? Well, that's going to be x to the 0 times C0 plus, now let's go back up and look at what happens for C sub 2. C sub 2 is equal to 3C sub 0. So that's going to be plus x squared times 3C sub 0. Now let's look at what happens with x to the 4th. So x to the 4th, we're going to go back up. We're looking at C4. Okay, well C4 is equal to C0. All right, so It's just going to be a C naught. Now let's look at C sub 6. So C sub 6 is going to be equal to negative 1/5 C naught. And then I think we did an 8 as well. And that's 3/35 C naught. Right? And that pattern, whatever it is going to go on forever. If we wanted to, we could get even more expressions out of that, right? We could just keep using the generating function to get, there should be an x to the 8, excuse me. All right, but we could get x to the 10, x to the 12. But remember, we looked at the idea that we ended up, I think, with like a 4th or 5th degree polynomial, and it did a pretty good job modeling the function earlier, right? So, one solution that we get, if we simplify all this stuff, is going to be C naught times the quantity of. So if we factor that out of here, that's just a 1 plus 3x squared plus x to the 4th minus 1/5 x to the 6th plus 3/35 x to the 8 plus ... All right, we're not sure what comes after that, but there's a pattern that's going on. And you can leave your solutions just in that form. That's perfectly fine. Now, what's the second solution? Well, that's when we have C1 terms. So these are going to be all of the odd terms for C. All right, so let's go all the way back up. Now remember, C1 is just C1. But we have that C3 is equal to C1. All right, so here's what we can write. C1 times x to the 1st plus C1x cubed. All right, and the reason we write that is because, remember we said C3, which is the coefficient of x cubed, is equal to C1. So we get an x cubed C1. Now we have C5 equals 0, so it's really 0x cubed, x to the 7th, x to the 9th. So it looks like the only terms that really matter, and I'm going to write these in just because we can. So this is going to be plus 0x to the 5th plus 0x to the 7th plus 0x to the 9th plus ... The only terms that really matter are going to be these first two. So y2 is going to be equal to, I'm going to factor out the C1, x plus x cubed. All right. So that one's pretty cool because we just get a polynomial term. This one ends up being an indefinite polynomial, a series. All right. So that's how we can identify those. All right. Now, what's really cool is we can actually check this one to make sure it works. All right. This one we can't really check because it's indefinite. All right. But let's just check. Let's just check this one because we can. All right. So x squared plus 1, y double prime, plus minus 6y. Remember, that's the original differential. Is equal to 0. Now we have that y is equal to, and I'm just going to distribute the c again. So that's c1x plus c1x cubed. Y prime, which we don't really need, is c1 plus 3c1x squared, and then y double prime is just going to be 6x c1. Let's plug those back in, and let's see if it makes any sense whatsoever. All right, so we're just going to plug this back in for y. We're going to plug this back in here. X squared plus 1 times 6x c1 minus 6 times the quantity of c1x plus c1x cubed equals 0. We're going to distribute, and that's going to wind up with 6x cubed c1 plus 6x c1. We're going to distribute negative 6. Negative 6x c1 minus 6c1x cubed. And does that equal 0? Let's hope so. Otherwise, we've just spent a half hour doing nothing. that cancels with this cancels with this, 0 equals 0. So one of two things happened. Either A, we got exceptionally lucky, we defined all of probability, and we just happened to stumble upon the right solution by pure luck, even though we did it wrong, or we did the right way. Let's go with the latter and suggest that we did it using the right way. All right, so if we want to write our final solutions to this, we certainly can. And so you could write the final solution to this in a couple ways. Now remember, we had a solution y1, and I'm just going to copy that just to save a little bit of time. All right, so we went all the way back up here. Remember, this was y1. I'm going to copy this down. I know I didn't write it out too well. Let me just paste this here. I'll delete it after I'm done. But y1 is going to be equal to c0 times 1 plus 3x squared plus x to the 4th minus 1/5 x to the 6th plus 1 over 35, or 3 over 35, excuse me, x to the 8th plus dot, dot, dot. All right, so that's y1. And for y2, well, we just showed that one works, so we can't be wrong about that one. Y sub 2 is going to be equal to c1 x plus x cubed. Do we want to know what y of x is? Well, the function y of x is going to be equal to c0 plus 3c0 x squared. Well, I guess I should put them in order of the x, which is the independent variable. So we could say plus c1x plus 3c0 x squared plus c1x cubed plus x to the 4th times c0. And so notice what I'm doing is I'm just putting these in ascending order of the x's. We don't have an x to the 5th, so we could just say minus 1/5 x to the 6th plus 3 over 35 x to the 8th plus dot, dot, dot. And this could be our final solution. All right. However, this usually makes a little bit more sense to have these as the two solutions. And when somebody asks you to give these solutions are linearly independent. Okay, so these are two linearly independent solutions. And linearly independent means that you can't write the one in terms of the other by multiplying it by a constant. All right, that's important because, as we know in vector spaces, that means we have a parallel vector space, and that just means they're dependent. These are completely linearly independent. All right, so I know it's a long problem, it's a difficult process, but this is the process we have to go through when we're utilizing variable coefficients to our second order differentials. Now in the next example, what we're going to do is we're going to take a look at a solution about a point different than 0, which we haven't seen yet. Very similar to what we just did, except there's going to be one major algebra trick that's going to be different.